November 12th, 1944. Normandy bocage, eastern France. American armoured divisions had broken through German lines 3 months earlier, racing across France faster than supply lines could follow. Operation Cobra's breakout in late July had shattered German defences. Patton's Third Army had liberated Paris by late August. By September, Allied forces stood at Germany's doorstep, having covered distances in weeks that World War I armies had failed to traverse in years. Then autumn rains began. The same meteorological pattern that had transformed Flanders into a swamp during the Great War now turned French and Belgian farmland into glutinous mud that swallowed tanks whole. Standard M4 Sherman tracks, 16.5 inches wide, had performed adequately during the summer campaign when French roads were dry and Norman fields were firm. Now those same tracks sank deeper, with every yard forward into soil that had absorbed 6 weeks of nearly continuous rainfall. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Ground pressure measured 14 pounds per square inch, enough to cut through Norman hedgerows during August. Too much to cross the liquid earth of a European autumn. The Sherman's 35-ton weight, distributed across tracks designed for North African desert warfare, exceeded the bearing capacity of saturated European soil. Each tank that attempted to maneuver cross-country sank hub-deep within minutes. What had been firm agricultural land in summer became an impassable barrier by November. Panther tanks with their 25-inch tracks glided across terrain where Shermans bogged down completely. The German advantage wasn't superior armour or firepower, it was physics. Weight distributed across wider tracks meant lower ground pressure. Panthers, despite weighing 10 tons more than Shermans at 45 tons, pressed only 8.8 pounds per square inch against soft ground. Shermans pressed 14. The 40% difference in ground pressure meant the difference between mobility and immobilization. Between tactical success and operational paralysis, the irony was brutal. American industrial capacity produced 5 Shermans for every Panther Germany manufactured. Allied forces enjoyed overwhelming numerical superiority in armour, but numerical advantage meant nothing when half the tanks couldn't reach battle positions. German forces, outnumbered and outgunned, maintained defensive lines simply by positioning themselves on firm ground and watching American armour bog down attempting to flank through soft terrain. Staff Sergeant Michael Donovan of the 2nd Armoured Division watched his platoon's 4th Sherman sink hub-deep into Belgian mud 5 miles south of Aachen. The tank's Ford GAA engine roared at maximum power, 500 horsepower churning 35 tons of steel armour deeper into European soil. The narrow rubber tracks spun uselessly, throwing rooster tails of mud 20 feet behind the tank while the hull settled inexorably earthward. Recovery would require hours of work. Steel cables attached to other tanks, wooden planks placed under spinning tracks, often another tank to provide pulling power, which risked bogging down a second vehicle. Meanwhile, German forces repositioned. Artillery ranged new targets. The tactical initiative shifted to an enemy who understood how weather transformed battlefields more effectively than any weapon. The mathematics of mobility had become brutally simple. First Army's armoured divisions averaged 8 miles per day during August's breakout across France. By mid-November, advance rates had collapsed to less than 2 miles daily. Not because German resistance had stiffened, not because American armour had been destroyed, but because 35-ton tanks equipped with tracks designed for desert warfare couldn't maintain traction in conditions that would have been familiar to any European farmer. Ordnance Corps engineers had anticipated many battlefield challenges when designing the M4 Sherman. They'd built a tank that could be manufactured by automobile plants. They'd created armour that could withstand German 75mm guns. They'd installed gyrostabilized sights that allowed firing while moving. But they hadn't adequately prepared for the fundamental reality of mechanized warfare in Northern Europe. Mud stopped tanks more effectively than German guns. Lieutenant Colonel James Morrison commanded 1st Battalion, 37th Tank Battalion, 4th Armoured Division. His unit had stormed across France with Patton's 3rd Army during Operation Cobra's breakout. By October, his battalion's operational readiness had dropped to 40%, not from enemy action, from stuck tanks, broken final drives, transmission failures caused by prolonged operation in first gear trying to maintain forward momentum through soup-thick mud. Morrison's after-action reports documented the grim arithmetic. 8 tanks bogged down per day required recovery operations. Recovery operations consumed 4 hours average per tank. Battalion maintenance crews worked 18-hour shifts, pulling vehicles from mud that German defenders never had to create. The ground itself had become Hitler's most effective defensive weapon since the hedgerows of Normandy. The problem wasn't unique to American armour. British Churchill tanks, with their wider tracks, performed marginally better in soft terrain, but lacked the Sherman's mechanical reliability. Soviet 34 tanks distributed weight more effectively, but weren't available to Western Allied forces. German Panthers had the mobility advantage, but suffered catastrophic mechanical failures that stranded them more effectively than any mud. October 19th, 1944. Detroit Arsenal Tank Plant, Warren, Michigan. Army Ordnance. Engineers convened emergency consultations on improving M4 mobility in soft terrain. The meeting brought together automotive engineers, military tacticians, and production specialists. Each group understood the problem from different perspectives. Frontline commanders needed solutions immediately. Production managers needed solutions that wouldn't disrupt existing manufacturing. Engineers needed solutions that would actually work under combat conditions. The problem was clear. Shermans needed lower ground pressure to operate in soft terrain. The solution appeared straightforward. Reduce ground pressure by increasing track width. But implementation faced enormous obstacles that made the straightforward solution anything but simple. Sherman suspensions used vertical volute spring systems, specifically designed around 16.5-inch tracks. The entire system, from road wheels to drive sprockets to suspension bogies, had been engineered as an integrated package. Change one component, and everything else required redesign. Widening tracks fundamentally required redesigning road wheels to accommodate increased width. Drive sprockets needed different tooth spacing to engage wider tracks. Suspension bogies required modified mounting points to handle altered load distributions. Hull mounting points had to be repositioned to accommodate wider track runs. Such modifications would delay production for 6 months minimum, while engineering teams redesigned components, manufactured prototypes, tested under field conditions, and retooled production lines. Meanwhile, frontline units needed solutions within weeks, not months. The vertical volute spring suspension itself presented additional complications. Each bogie unit consisted of 2 road wheels mounted on a vertical volute spring that absorbed shock loads. The springs were calibrated for specific track widths and loads. Wider tracks meant different load distributions that would overstress existing springs, requiring completely new suspension units. The cascading engineering requirements threatened to transform a simple track modification into a comprehensive vehicle redesign. Captain Robert Henderson, a pre-war automotive engineer from Ford Motor Company, proposed the most radical solution during the afternoon session on October 20th. His background wasn't in military engineering. He'd spent 10 years designing agricultural equipment before the war. Tractors, combines, heavy machinery that operated in exactly the kinds of soft soil conditions that now plagued Sherman operations. His perspective was practical rather than theoretical. Don't redesign the tracks. Modify the connectors. Each Sherman track consisted of 79 individual steel shoes, connected by end connectors that held track pins together. What if those end connectors could be extended outward with simple bolt-on plates? Additional width without fundamental redesign. Field installable modifications that didn't require factory retooling. The concept violated conventional engineering wisdom. Proper track design integrated all components as a unified system. Bolt-on extensions seemed improvised, temporary, inadequate for the stresses of armoured warfare. But Henderson's proposal had one overwhelming advantage. It could be implemented immediately using existing manufacturing infrastructure. Small steel fabrication shops throughout England and France could produce track extensions without disrupting main tank production. Ordnance-approved field trials on October 23rd. 2 M4A4 tanks received prototype extended end connectors at the Aberdeen Proving Grounds in Maryland. The extensions added 4 inches of width to standard tracks. Total track width increased from 16.5 inches to 20 inches. Ground pressure dropped from 14 pounds per square inch to 11.5. A 20% reduction that transformed mobility in conditions where every pound of pressure determined success or failure. The test course replicated European autumn conditions. Sections of swamp flooded to saturation. Clay soil churned into consistency, matching French farmland after weeks of rain, obstacles that standard track Shermans couldn't negotiate without assistance. The modified tanks would either prove Henderson's concept or confirm conventional wisdom that proper engineering required comprehensive redesign. November 2nd, 1944. Aberdeen Proving Grounds. The first modified Sherman approached the swamp section at 8 miles per hour. Standard procedure called for reducing speed to maintain traction. The test driver ignored protocol. He needed to know if extended connectors provided enough additional flotation to maintain momentum through terrain that stopped unmodified tanks cold. The Sherman's nose dipped as front tracks contacted saturated ground. Mud fountained behind spinning tracks. For 3 seconds, the tank appeared to be settling into the characteristic hull-deep bog that plagued operations in Europe. Then the extended connectors bit into subsurface clay layers beneath the liquid mud. The wider footprint distributed weight across larger surface area. Ground pressure remained below the threshold, where soil liquefied under track loading. The Sherman maintained forward momentum. Not gracefully, not quickly, but continuously. The tank crossed 80 yards of swamp in third gear without assistance. An unmodified M4A3 test vehicle attempted the same crossing immediately afterward, using standard 16.5-inch tracks. It bogged down completely within 30 feet, requiring 2 recovery vehicles and 4 hours to extract. The test results were sent by courier to Supreme Headquarters Allied Expeditionary Force the same afternoon. General Eisenhower's staff calculated that improved mobility could accelerate the advance toward Germany by weeks. Every day saved meant fewer casualties, less time for German forces to consolidate defenses. The potential strategic impact of a simple track modification exceeded the tactical value of entire tank battalions. But mass production presented enormous challenges. Each Sherman required 158 extended end connectors. First Army alone operated over 4,000 Sherman tanks. Meeting demand required producing over 600,000 track extensions immediately. American factories could tool up for such production. But manufacturing in the United States meant shipping finished components across the Atlantic. Delivery would take months. Frontline units needed solutions within weeks. The answer came from an unexpected source: French civilian contractors. Small metalworking shops throughout liberated France possessed welding equipment and steel supplies suitable for producing track extensions. These shops had manufactured agricultural equipment, construction materials, and civilian goods before the German occupation. Now they could contribute directly to liberation by producing military hardware that didn't require specialized knowledge or sophisticated tooling. Ordnance negotiators contracted with 63 French metalworking firms during the first week of November. Each shop received detailed blueprints for extended end connectors. The design specifications were intentionally simple. Rectangular steel plates 4 inches wide by 5 inches long, 1/4 inch thickness. 2 mounting holes precisely positioned to match standard Sherman end connector bolt patterns. Corner radius requirements to prevent stress concentrations. specifications that competent metalworkers could meet without aerospace-grade precision. Payment was arranged through military scrip redeemable for American cigarettes, chocolate rations, and fuel allocations. French contractors accepted these terms eagerly. The work provided income when normal economic activity remained disrupted by war. More importantly, it offered tangible contribution to liberation. Every track extension produced was one more component, helping American tanks push German forces back toward the Rhine. Production began on November 8th. Initial output rates disappointed ordnance planners. The first week yielded only 12,000 extended connectors, enough for 76 tanks. At that rate, equipping First Army's Sherman force would require over a year. But production curves improved rapidly as French shops optimized workflows and trained additional workers. By November 20th, weekly output had increased to 48,000 connectors. By December 1st, 80,000 per week. Quality control became the critical challenge. Extended connectors had to withstand tremendous mechanical stresses. Sherman tracks experienced shock loads exceeding 30,000 pounds when crossing obstacles at speed. Improperly manufactured extensions would break off under combat conditions. Worse, failure during movement could jam tracks and immobilize tanks under enemy fire. Every connector required inspection before installation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Ordnance established quality control stations at supply depots throughout France and Belgium. Inspectors tested random samples from each contractor by loading extensions to failure. Acceptable specifications required withstanding 40,000 pounds without fracturing welds or deforming mounting holes. Contractors whose products failed inspection lost contracts immediately. The combination of economic incentive and rigorous standards maintained production quality despite wartime urgency. Tank crews received their first extended end connectors during the third week of November. Installation required no specialized tools or training. Each connector bolted directly onto existing track end connectors using standard half-inch bolts. A competent crew could modify an entire track in 4 hours. Most battalions performed modifications during routine maintenance when tracks were removed for inspection anyway. The connectors acquired their nickname almost immediately. American tankers called them duckbills because the rectangular steel plates extended outward from tracks like waterfowl feet. The name was informal, unofficial, never appeared in technical manuals, but it spread through armored divisions faster than official nomenclature. Within 2 weeks, every tank crew in First Army knew exactly what duckbills were and why they mattered. December 11th, 1944. First Army's armor regiments had modified 73% of their Sherman tanks with extended end connectors. The timing was brutally fortuitous. German forces were preparing their final major offensive on the Western Front, Operation Wacht am Rhein. The assault that Allied intelligence completely failed to anticipate. The attack that American soldiers would remember as the Battle of the Bulge. The Ardennes forest of Belgium seemed an unlikely location for armoured warfare. Heavily wooded terrain cut by deep ravines, narrow roads threading between villages. Exactly the kind of restricted terrain where defenders held every advantage. But German planners had studied weather patterns carefully. Early December typically brought the Ardennes' first hard freeze. Frozen ground would support tank movement cross-country. The window between autumn mud and winter snow presented Germany's last opportunity to concentrate armoured reserves for decisive offensive action. Hitler's gamble required maintaining momentum. German forces needed to advance 60 miles in less than a week. Seize bridge crossings over the Meuse River before Allied reinforcements could respond. The plan's success depended on rapid movement that didn't bog down in tactical engagement. Speed over firepower, momentum over positional warfare, the kind of blitzkrieg that had worked so effectively in 1940 against France, but hadn't succeeded anywhere since Stalingrad. First Army's defensive positions in the Ardennes were thinly held, 4 divisions covering 85 miles of front. A calculated risk based on intelligence estimates that German forces were too weak for major offensive operations. When 13 German divisions supported by 7 panzer divisions attacked before dawn on December 16th, American units found themselves overwhelmed by forces they hadn't known existed. The initial German assault achieved complete tactical surprise. American defensive lines collapsed within hours. Entire regiments found themselves surrounded. Communication networks failed as German forces overran command posts. The situation resembled the early days of the German invasion of France, except this time, American forces were on the receiving end of catastrophic operational failure. But something unexpected began happening by the second day of the offensive. German armor started experiencing exactly the mobility problems American forces had suffered throughout November. The Ardennes' early freeze hadn't materialized. Instead of frozen ground, unseasonably warm temperatures produced mud. German panthers and tigers, pressing their weight against Belgian soil softened by rain, began bogging down with the same mechanical regularity that had plagued Sherman operations for months. The difference was that Sherman crews now had duckbills. The extended end connectors that seemed like improvised field expedients became the tactical edge that German armor couldn't match. When American forces counterattacked to relieve surrounded units, their modified Shermans maintained momentum through terrain, where German armor bogged down helplessly. The technological balance had shifted in ways that nobody at Supreme Headquarters had predicted, and German intelligence had completely failed to anticipate. Sherman Duckbills, Script, ASA, Part 2 Final, December 20th, 1944. Bastogne, Belgium. The strategic crossroads town controlled 7 major roads, radiating outward like spokes on a wheel. Control Bastogne, and you controlled movement throughout the southern Ardennes. German forces understood this. American forces understood this. The town had been completely surrounded by German forces for 4 days. Brigadier General Anthony McAuliffe and the 101st Airborne Division held defensive positions against overwhelming German forces. 11,000 American soldiers faced 45,000 Germans, 5 panzer divisions, 2 panzer grenadier divisions, Volksgrenadier infantry, artillery that outnumbered American guns 3-1. Supply was down to minimum rations, 10 rounds per artillery piece, 1K ration per man per day, ammunition running critically low, most rifle companies operating with less than 60% of standard ammunition allocation, medical supplies exhausted. The division surgeon was performing amputations without anesthesia. Morphine had run out on December 18th. The weather prevented aerial resupply. Heavy cloud cover at 800 feet made parachute drops impossible. C-47 transport aircraft couldn't risk flying below cloud deck into concentrated German anti-aircraft fire. Relief seemed impossible. German commanders had offered surrender terms on December 22nd. A formal note delivered under white flag demanded immediate capitulation to avoid complete destruction of Bastogne's garrison. McAuliffe's response became legendary. Nuts. One word that summed up American determination to hold regardless of odds. But determination didn't solve supply problems. McAuliffe's forces could hold another 3 days maximum before ammunition shortage forced withdrawal or surrender. After that, German forces would control the road network, and Allied counteroffensive would face enormously complicated logistics. General Patton's Third Army had been ordered to break through German lines and relieve Bastogne before German forces could reduce the town through sustained assault. The mission required moving armoured divisions 60 miles through hostile territory in winter conditions, a task that would have been difficult under ideal circumstances. In the mud and ice of the Ardennes, it seemed suicidal. Every staff officer calculating approach routes concluded that relief couldn't arrive in less than a week. McAuliffe's surrounded forces didn't have a week. 4th Armoured Division's 37th Tank Battalion drew the spearhead assignment. Lieutenant Colonel Creighton Abrams commanded the lead combat command. His Sherman tanks had been modified with extended end connectors during late November as part of routine maintenance. At the time, the modifications seemed like incremental improvements to solve persistent mobility problems. Nobody anticipated they would determine whether surrounded paratroopers lived or died. The relief column moved out from Arlon on December 22nd. Abrams' tanks pushed north through roads, choked with retreating American units and civilian refugees. German artillery fire harassed the column constantly but couldn't stop forward momentum. The real enemy was terrain, secondary roads barely wide enough for single-file tank movement, shoulders softened by rain that collapsed under track loading. Every mile forward risked bogging down lead vehicles and stranding the entire column. German forces had positioned blocking groups at every road junction. Panthers hull down behind stone walls, anti-tank guns sighted to cover approach routes, Panzerfaust's teams waiting in buildings. The defensive positions were textbook perfect. Under normal circumstances, breaking through would require methodical preparation, artillery bombardment, infantry reconnaissance, careful coordination, time that McAuliffe's surrounded forces didn't have. Abrams' solution violated every tactical doctrine in the choir. Manual, maximum speed, continuous fire, no stopping for anything. His lead Sherman, commanded by Lieutenant Charles Boggess, would simply drive straight through German defensive positions without pausing to engage. The tanks behind would suppress flanking fire. Infantry following in half-tracks would mop up bypassed positions. The strategy worked only if lead tanks maintained momentum regardless of ground conditions. The column hit the first German blocking position at Martelange at 1400 hours. 2 Panthers positioned to command the bridge crossing. German gunners had perfect firing positions and excellent fields of fire. They opened up at 800 yards. Their first shots destroyed the lead American half-track and damaged a following Sherman. Standard procedure called for deploying infantry, calling artillery, and reducing the position methodically. Abrams ordered Boggess to accelerate through the kill zone. The modified Sherman's duckbill-equipped tracks bit into the muddy approach. Standard tracks would have spun out, trying to maintain speed on the slope leading to the bridge. The extended connectors provided enough additional traction to keep the 35-ton tank accelerating through German fire. Boggess's gunner, Corporal Homer Davis, fired the 76mm gun on the move. The gyro-stabilized sights kept the gun trained forward, even as the Sherman bounced over uneven ground. A German 75mm round struck Boggess's turret at 20 degrees deflection. The shot ricocheted off sloped armor, gouging a deep scar but failing to penetrate. The Sherman crossed the bridge at 20 miles per hour, while German infantry scattered from positions they'd considered impregnable. The momentum carried through what should have been an 8-hour fight in less than 7 minutes, not because of superior firepower or better tactics, because modified tracks maintained traction where standard equipment would have failed. Patton repeated at Vernon, at Chaumont, at every German blocking position between Arlon and Bastogne. Modified Shermans maintained speed through terrain where unmodified tanks bogged down. The Germans had positioned their defences, assuming American armour would be channeled onto hard surface roads where anti-tank guns could engage at optimal range. Instead, duckbill-equipped Shermans cut cross-country through soft ground that German planners considered impassable to armour. By December 26th, 4th Armoured Division had covered 62 miles in 4 days. An advance rate that staff planners had calculated was impossible given terrain and weather conditions. At 1630 hours, Boggess's lead Sherman crashed through German lines into Bastogne's defensive perimeter. The 101st Airborne was relieved. German forces around Bastogne found themselves suddenly defending against attacks from both inside and outside their encirclement. The relief of Bastogne became the turning point of the Battle of the Bulge. German forces had achieved initial surprise and tactical success, but they couldn't maintain the rapid advance their operational plan required. Panther and Tiger tanks, superior to Sherman's in firepower and armour, bogged down in mud that their wider tracks couldn't overcome, because German engineers hadn't anticipated weather conditions. American Shermans with improvised track extensions maintained mobility. German armor couldn't match. January 15th, 1945. Aberdeen Proving Grounds conducted comprehensive comparative mobility trials that would define understanding of armored vehicle performance in soft terrain for decades. The tests involved American M4 Shermans with various track configurations alongside captured German Panther OSF-G and British Churchill Mark 7 tanks. The trials course replicated Ardennes conditions with scientific precision. Sections of swamp flooded to saturation, then precisely measured for consistency. Clay soil churned into exact consistency, matching French farmland samples analyzed in laboratory conditions. Obstacles that standard track Shermans couldn't negotiate without assistance. The modified tanks would either prove Henderson's concept or confirm conventional wisdom that proper engineering required comprehensive redesign. The testing protocol was exhaustive. Each tank configuration received identical evaluation criteria. Flotation measured by depth of track sinkage under static load. Traction measured by maximum slope angle sustainable before track slippage occurred. Speed sustainability measured by ability to maintain forward momentum through soft terrain. Durability measured by track component failure rates after repeated obstacle crossings. The trials would generate quantifiable data rather than anecdotal field reports. Standard Sherman tanks with 16.5-inch tracks performed worst in flotation trials. They sank deeper into soft ground than any other vehicle tested. Average track penetration measured 18.3 inches into standardized soft soil. For comparison, the same soil supported only 12.1-inch penetration from Panther tracks. The 40% difference in sinkage directly correlated to ground pressure differentials. Higher pressure meant deeper penetration. Deeper penetration meant increased rolling resistance. Increased resistance meant higher fuel consumption and reduced operational range. Panthers, with their 25-inch tracks, showed the best flotation characteristics in static testing. They sank least in saturated soil, barely pressing into the surface layer. But static testing told only part of the story. Dynamic testing, with tanks actually moving through soft terrain, produced dramatically different results. The wide Panther tracks that distributed weight so effectively under static conditions provided surprisingly poor traction when attempting to maintain momentum through variable terrain. The physics explained the paradox. Wide, smooth tracks maximized contact area with soft ground. But maximum contact area meant maximum surface friction that worked against forward motion when tracks encountered variable resistance. Panther tracks, designed to minimize ground pressure for weight distribution, inadvertently maximized surface drag when operating in conditions where soil consistency varied from one yard to the next. The tank that sank least also gripped least effectively, but traction trials produced opposite results that reversed every assumption from flotation testing. Panthers spun their tracks helplessly on muddy slopes that modified Shermans climbed in second gear. Test runs up a 15-degree incline covered with 6 inches of mud demonstrated the difference dramatically. Standard Shermans made it 9.2 meters before losing traction. Panthers, with their superior flotation characteristics, lost traction at 6.8 meters. Modified Shermans, with extended connectors and additional grousers, climbed the entire 30-meter test slope without slippage. The explanation lay in track design philosophy. German engineers had optimized Panther tracks for weight distribution across maximum surface area. American engineers, working within constraints of bolt-on modifications, had inadvertently optimized for traction through increased edge loading. The extended connectors created pressure points that dug into soft soil rather than riding across the surface. Combined with grouser teeth that bit into subsurface layers, modified Sherman tracks achieved mechanical grip that smooth, wide Panthers couldn't match. Shermans equipped with extended end connectors and additional grousers performed best overall in combined testing. They achieved 91% of Panther flotation while providing 130% of Panther traction. Speed sustainability testing showed modified Shermans maintained forward momentum at 8 miles per hour through terrain that stopped Panthers completely at 4 miles per hour. The modifications that had seemed improvised and temporary proved superior to purpose-built German engineering for the specific conditions of Northwest European winter warfare. Durability testing revealed the modifications' primary weakness. Extended connectors failed at an average rate of 2.3% per 100 miles of operation on mixed terrain. Hard obstacles like rocks or concrete debris broke them off. Track tension variations caused by uneven wear loosened mounting bolts. The quarter-inch steel plates deformed under repeated shock loading from high-speed obstacle crossings. Panthers, despite their mechanical unreliability in other systems, showed zero track extension failures because they had no bolt-on components to break. But the failure rate was considered acceptable given the tactical advantages. Tank crews carried spare extended connectors as routine load. Installation required 15 minutes per failed unit. Compared to recovering a bogged tank, which required hours and specialized equipment, replacing broken track extensions was trivial maintenance. The trade-off between durability and capability strongly favored the modified design. British 8th Army conducted similar trials on March 6, 1945, using captured Panthers alongside modified Shermans. The test course included a steep, hard surface slope, a 9 to 14-foot wide ditch filled with standing water, and an 80-yard muddy field that had been repeatedly ploughed and watered to create maximum difficulty. Every tank was required to climb the slope, cross the ditch, and traverse the field without assistance. The Panther climbed the hard slope easily, crossed the ditch successfully, but bogged down completely in the muddy field. The tank's driver attempted to reverse out of the predicament, but the gearbox jammed under load. The Panther required 2 recovery vehicles and 8 hours to extract. Churchill tanks performed marginally better, crossing the ditch and making partial progress through the field before requiring assistance. Shermans with extended end connectors and platypus grousers completed the entire course in second gear without difficulty. The modified American tanks finished the course in 97 seconds. Standard Sherman took 341 seconds and required help crossing the ditch. The trials definitively demonstrated that field-expedient modifications had solved mobility problems that purpose-built German armour couldn't overcome. But extended end connectors had significant drawbacks that became apparent through combat use. The bolt-on extensions were fragile. Any impact against hard obstacles broke them off. Tanks operating in urban terrain lost duckbills constantly when tracks scraped against stone buildings or cobblestone streets. The extensions also threw tremendous amounts of mud when tanks operated in soft ground. Engine decks became coated with debris that clogged cooling systems and created fire hazards. The added weight, 317 kilograms per tank, stressed suspensions designed for lighter loads. Vertical volute spring systems that had performed adequately with standard tracks now required more frequent maintenance. Road wheels wore faster under increased lateral loading. Track pins elongated more rapidly, requiring constant adjustment to maintain proper tension. The modifications extended Sherman mobility at the cost of increased maintenance burden. Tank crews adapted quickly to working around these limitations. Extended end connectors were installed only when operating in soft terrain. When units moved to urban areas or hard surface roads, crews removed the extensions and operated with standard tracks. This flexibility was the modification's greatest advantage over purpose-built wide-track systems. Panthers couldn't change track width based on terrain. Modified Shermans could adapt to conditions in hours. Production of extended end connectors peaked in January 1945 at over 120,000 units per week. French contractors were producing components faster than American units could install them. Ordnance established forward supply depots throughout Belgium, France, and Luxembourg, where tank battalions could pick up pre-packaged track extension kits without requisitioning through normal supply channels. The distribution system ensured every Sherman crew had access to modifications when needed. German intelligence reports captured after the war revealed complete confusion about American track modifications. Wehrmacht technical intelligence sections couldn't understand how Sherman suddenly achieved mobility advantages over German armor in conditions that should have favored wider track Panthers. Some reports speculated Americans had developed entirely new suspension systems. Others suggested Allied forces were receiving new tank models not previously identified. The reality that simple bolt-on track extensions provided the advantage never appeared in German intelligence assessments. The extended end connector program demonstrated industrial mobilization advantages that Germany couldn't match. American forces identified a tactical problem in November, developed a solution, initiated mass production, and fielded modifications to thousands of tanks by January. The entire cycle from problem identification to operational deployment took less than 3 months. German procurement systems couldn't have responded that quickly, even if Hitler's regime had been willing to admit tactical deficiencies required correcting. By February 1945, over 68% of First Army's Sherman tanks operated with extended end connectors. Third Army reached 72%. Ninth Army, operating in the northern sector where mud was particularly severe, achieved 83% coverage. The modifications had transitioned from experimental field expedient to standard operational practice in less than 4 months. The push toward the Rhine in February and March demonstrated how thoroughly extended connectors had transformed American armor operations. Sherman battalions maintained advance rates, averaging 12 miles per day through terrain that had limited progress to 2 miles daily during November. The improvement wasn't because German resistance had weakened or because spring brought better weather. February was actually worse than November in terms of ground conditions. The difference was that American tanks now had traction Germans couldn't match. Operation Grenade, the Ninth Army's Rhine crossing in late February, relied heavily on modified Sherman mobility. The operation required crossing 60 miles of saturated Ruhr River floodplain, where German engineers had deliberately flooded fields to create impassable barriers to armor. Staff planners calculated that unmodified tanks would require 2 weeks to traverse the flooded zone. Modified Shermans crossed in 5 days, maintaining pressure on retreating German forces that couldn't establish new defensive lines quickly enough to slow American advance. The strategic impact of extended end connectors exceeded anyone's initial expectations. A modification designed to solve tactical mobility problems had cascading effects throughout operational planning. Commanders could schedule advances, assuming Sherman units would maintain momentum through soft terrain. Artillery could plan fire support, assuming armored spearheads would reach objectives on time. Infantry could coordinate attacks, knowing tank support would arrive when needed. The reliability transformed how entire armies operated. But the extended end connector was always understood to be a temporary expedient. The long-term solution to Sherman mobility limitations was the horizontal volute spring system, HVSS suspension, with 23-inch tracks that provided superior flotation and dramatically improved ride quality. HVSS-equipped Shermans, nicknamed Easy 8s, began reaching Europe in December 1944, but production couldn't match demand until March 1945. Easy 8 Shermans, with their wider factory tracks and improved suspension, represented the culmination of American tank development during World War II. They rendered extended end connectors obsolete for new production. But HVSS couldn't be retrofitted to existing vertical volute suspension Shermans. The thousands of older model tanks already in Europe would continue operating with duckbills through the end of the war. The Rhine crossings in March demonstrated both the capabilities and limitations of extended connector technology. Modified Shermans maintained traction on muddy approaches to crossing sites where unmodified tanks bogged down. But the modifications provided no advantage once tanks reached German territory east of the Mothis, the Rhine, where spring ground conditions were generally firm. Many units removed their extended connectors after crossing the river and never reinstalled them. German surrender in May 1945 ended the European war before comprehensive analysis could determine exactly how much extended end connectors had contributed to Allied victory. Operational research sections attempted post-war studies, but the data was too complex to isolate track modifications from dozens of other factors affecting campaign outcomes. Weather, German force dispositions, Allied air superiority, fuel shortages, political decisions. All influenced results in ways that couldn't be mathematically separated. What was undeniable was that American tank crews universally praised extended connectors. After-action surveys conducted in April 1945 showed 93% of Sherman commanders considered duckbills essential equipment for soft terrain operations. 87% reported that track modifications had prevented their tanks from bogging down in situations where unmodified vehicles would have been immobilized. The field-level consensus was overwhelming. The modifications worked exactly as intended. The extended end connector never received the recognition of more dramatic innovations like Bailey bridges or Cullen hedgerow cutters. Military histories of World War II rarely mentioned the modification beyond technical appendices, but tank crews who fought through the Ardennes winter and Rhine spring understood the prosaic truth. Battlefield success often depended less on dramatic technological breakthroughs than on solving practical problems with simple solutions implemented quickly. The duckbill story illustrated fundamental principles about military innovation. Complex problems didn't always require complex solutions. Field expedients sometimes performed better than purpose-built systems. Industrial flexibility mattered more than engineering perfection. Speed of implementation trumped comprehensive testing. The American military establishment's willingness to accept imperfect solutions that could be fielded immediately gave Allied forces advantages that German dedication to engineering excellence couldn't match. French contractors who produced track extensions never received medals or official recognition. Their contribution was purely industrial, making thousands of steel plates to exact specifications under time pressure. But those anonymous metal workers in Lyon and Marseille and Toulouse had contributed as directly to liberation as any infantry division. Their work kept American armor mobile when weather and terrain conspired to bog down offensive operations. They'd turned German defensive advantages into Allied opportunities through nothing more sophisticated than rectangular steel plates welded to track connectors. By war's end, French contractors had produced over 4.7 million extended end connectors, enough to modify every Sherman tank in Europe 7 times over. The surplus created post-war diplomatic complications when French firms demanded payment in hard currency instead of military scrip. Eventually, the U.S. Army settled accounts through equipment transfers and reconstruction contracts. The fiscal details disappeared into occupation bureaucracy. The tanks those extensions helped carry across Europe remained visible monuments for decades. The extended end connector program's greatest legacy wasn't the modification itself. It was demonstrating that military organizations could adapt quickly when necessity demanded it. The U.S. Army in 1944 wasn't known for rapid innovation or flexible decision-making, but faced with tactical crisis, the institution had identified a problem, developed a solution, and fielded it across thousands of vehicles in months. The capacity for rapid adaptation would influence American military culture long after the last duckbill-equipped Sherman was decommissioned. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.